We've already looked at intrinsic magnetic fields in materials such as iron, where the spin on, or the magnetic moment of the electrons produces this magnetic field. Well, it turns out that moving charges, so moving electric charges, actually creates a magnetic field of its own. So it turns out that magnetic fields are actually just a consequence of the effects of special relativity on the moving charges, so the electric fields due to these moving charges. We don't need to worry about that here, but it's really interesting to point that out. So what does this look like? It looks like this. If we've got a current carrying wire, not a current carrying wire, a current carrying wire over here with the current going in that direction, and you could draw the magnetic field around that wire, it looks like it's coming out of the wire on this side, and that would be off into the space around it as well, and it would be going into the page on this side. And that's, you'll recall, the crosses and the dots represent a field going away from us and towards us respectively. You can work out which direction the magnetic field will be going on which side of the wire by using what's called the right-hand rule, and I'll show you how that works. So if I put my right hand and I wrap the right hand around that wire with my thumb pointing in the direction of the current, then my fingers will wrap around in the direction of the magnetic field. So if you do that, pretend you've got a wire in front of you and your fingers will curl around and they'll be coming out of the page up the top and into the page down the bottom. So that's what you need to do to figure out what the direction of the magnetic field is around a current carrying wire. Of course, we can draw this in another way. We can draw it with the current in a wire coming out of the page, and I'll do that now. So here's our wire, and I'll draw a dot to say that the current is coming towards us. And now I'll draw the magnetic field going around that wire. And again, if you use the right-hand rule with your thumb coming out of the page and your fingers wrapping around it, you'll see that the magnetic field is wrapping around in that direction. And I'll do the same for a wire current going into the page. Of course, you can write an equation for this, as you can for everything in physics, or almost everything in physics. If we've got the magnetic field B, we can show, or it can be shown, and that's what they discovered, was that it was the size of the magnetic field around that wire was proportional to the current in the wire, and inversely proportional to the distance from that wire. And there were some constants here. This is called the magnetic permeability of a vacuum, mu0, and there's a 2 pi in here as well. So just to review, the magnetic field strength B here, so the field strength in the region surrounding the wire, is directly proportional to the current. That means that as the current increases, the magnetic field also increases. the magnetic field strength B is inversely proportional to the distance from the wire. That means as we go further and further away from this wire in either direction, so further and further away from this wire, the magnetic field drops off as 1 over the distance. And that's why I've drawn these magnetic field lines further apart as we're getting further away from the wire, to signify that the magnetic field strength is getting weaker. Applying this equation is pretty straightforward, and we'll do some practice with that in class.